Okay, so the last thing I'll mention is some important theorems about power functions that we get out of this connection between holomorphic and analytic. It's not a deep connection, so recall we had power functions defined as z to the alpha, or in this case I have 1 plus z to the alpha. You have to have e to the alpha times a branch of log of what you're exponentiating. So here I'll use principal log. And so therefore, I need 1 plus z to not be on the negative real line. So that leaves me with this domain. And so we've already proven that the branches of log are analytic. So they're holomorphic. So e to them is just a composition of holomorphic functions. So holomorphic is the same as analytic. So these have to be analytic. What are their power series? Well, we can compute them with a very old theorem, Newton's binomial theorem, which is actually quite an amazing theorem because it just so surprisingly generalizes the standard binomial theorem. So if I have 1 plus z to the alpha, it has a power series with these binomial coefficients, but alpha may not be a positive integer, it's just a complex number here, but we can write it in a way that works for positive integers and just complex numbers. So I would take alpha times alpha minus 1 all the way down to alpha minus n minus 1. So I have n terms here. And it's like we're chopping off the rest of the terms, starting at alpha minus n, but that doesn't really make sense for a complex number. And then I divide by n factorial. So this is the theorem, and you've probably seen it in a calculus class. But let's just give some examples of it and prove it. Also, it's worth pointing out that you get a really interesting analytic function in two variables out of this. So if I write it this way, f of z comma w is 1 plus z to the w, well, the formula above is actually an absolutely convergent double power series because when I put in modulus of w into here, it's not too hard to check that you'll either get, coefficients here that are all of one sign or eventually of one sign, or else they alternate in a simple way. And so you'll get that this is analytic in z and w for z in the disk and w in the complex numbers. Okay, well, let's look at some examples. We've already done this by hand, but the binomial theorem gives it pretty quickly. Maybe I shouldn't go through the details. I'll just point out that you can apply the binomial theorem, Newton's binomial theorem, to 1 over 1 minus z to the m plus 1, where m is a natural number, and get the formula that we've had before down here. So this is just a good check. Let's look at 1 minus z to the negative 1/2, which you've probably done in calculus. So I put 1 minus z to the minus 1/2 in here. So I have this binomial coefficient minus 1/2, choose n. And I'm putting in minus z, so I have minus 1 to the n, z to the n. And then you can check what these terms look like. You'll have minus 1/2, minus 1/2 minus 1, all the way down to minus 1/2 minus, and minus 1. And if you keep track of all the signs, I guess all of these will be negative, so I'll have minus 1 to the n, and then I'll have a product of odd terms, a power of 2, and an n factorial here. Well, there's lots of little tricks for kind of turning this into something more familiar. What we can do is try to put in all the terms on top to make it 2n factorial. So essentially what you need to do is multiply the top and bottom by 2 to the n factorial. And I already have a 2 to the n down there. So I'll get 4 to the n, I'll get n factorial squared because I already have 2 n factorials. Okay, but this is pretty quick to go through. I recommend going through it yourself. But I'll get 2n, choose n, divided by 4 to the n, and this minus 1 to the n. When I put this back in here, the minus 1 to the n's disappear, and we get this nice formula for 1 minus z to the negative 1/2. Okay, so let's prove the theorem. We're basically going to prove it via differential equations. So we'll write out this power series that we claim is the right formula. Note that if alpha is a natural number, then f is just a polynomial because eventually these terms are all 0. So let's not do that case. Let's look at alpha not a natural number. Then you can do the ratio formula for the radius of convergence. I can do alpha, choose n plus 1, over alpha, choose n. And if you compare the terms, I guess I'll have alpha, alpha minus 1, all the way down to alpha minus n over n plus 1 factorial on the top, and on the bottom I'll have alpha, alpha minus 1, all the way down to alpha minus n minus 1. And we just have to compare these two things. I'll get an n minus 1 on the bottom, and then all these terms will cancel except the alpha minus n. And then as n goes to infinity, this just goes to 1. So the radius of convergence would be the 1 over 1, which would be 1. Okay, so it converges and it's a nice analytic function. Now we're going to show that capital F and little f, namely little f is this. Capital F and little f satisfy the same differential equation. So with little f, that's the differential equation is easy to get just from the chain rule. So little f is equal to e to the alpha log 1 plus z. So I take the derivative of that using the chain rule. So I'll get the original times the derivative of alpha log 1 plus z, which will give me alpha over 1 plus z. And so now I have f times alpha over 1 plus z. I want to show capital F satisfies the same formula, and that's just a matter of some formal stuff. And I don't know if I want to bore you with the details, but you take capital F prime, you'll get, when you take the derivative, an n and a z to the n minus 1. There's various shifting of indices and so forth. Maybe this is better just to try yourself. And we're trying to kind of match these differential equations. So I'll take, it's maybe too difficult to try to take capital F times this and see what we get. So instead I'll move this 1 plus z to the other side in my attempt. So you can easily manipulate these two power series, 1 plus z times capital F prime here. And if you work through it, you do indeed get alpha times capital F. So this shows that little f and big F satisfy the same differential equation, and we can just use a little trick then to show that they're the same. So capital F divided by little f, if I take the derivative using the quotient rule, will be this, but this will end up being identically 0 because I have f and then capital F alpha 1 plus z minus capital F little f alpha 1 plus z over f squared, but the top is just 0. Okay, so the derivative of this is identically 0. So this has to be constant, and so I'll plug in 0 to get 1. So this function is identically 1. So we get that the power function is equal to Newton's binomial formula.